Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the extrinsic semiconductors. As its name suggests, the extrinsic semiconductors are made by doping the external elements. Generally, the external elements are of group 15 and group 13 into the crystal of group 14 elements such as silicon, germanium, and carbon. So this process of adding impurity in the crystal is called as doping, and generally the concentration of doping is 1 ppm, which means that it is 1 atom of external impurity per million atom of base material. Now the biggest advantage of extrinsic semiconductor is the fact that we can control the conductivity of extrinsic semiconductor by controlling the amount of doping, because if we have to increase the external conductivity of the crystal, in fact conductivity of the crystal, we can increase the number of charge carriers by increasing the doping concentrations. Now on the basis of the majority charge carriers, it is classified, extrinsic semiconductors are classified into two forms, which is first is p type and second is n type. Now in p type semiconductors, you can see that in these semiconductors, group 13 elements such as aluminium is doped into silicon crystal or germanium crystal, which are group 14 elements. And as you know that aluminium only has 3 electrons in the outermost shell, one side of the bond is left vacant and a hole is formed at this point. So this aluminium just attracts this neighboring electron and becomes negatively charged, and therefore we call this aluminium or any other atom which is doped into this material as acceptor ion. Now why we are calling it as acceptor ion is due to the fact that it has accepted one electron and it has become the negatively charged. And there at this position, if the electrons has shifted to this position, a hole will be formed at this position. And in the same way, one aluminium is making one hole. So if we have use the concentration of aluminium as n, so n number of more holes will be formed in the crystal. So we know that hole is always situated in the bond, so we will always represent the hole inside the valence band, because valence band represents the lower energy level, and this is this is the electrons in conduction band. Now when this crystal was intrinsic, which means that when there was no doping done in the crystal, then there were some electrons in the conduction band and equal number of holes in the valence band, because due to the thermal agitation. Thermal agiation is a process in which electron gets sufficient amount of energy and it jumps to the conduction band, or in simpler words we can say that electrons break their covalent bonds and becomes free. So before the doping, there were some electrons in the conduction band and equal number of holes in the valence band. But after doping, the number of holes becomes very larger than the number of electrons, and this is due to the fact that the external atom which we have doped is bringing one hole per atom. So if we are keeping the doping concentration to a very high level, then we can say that the number of holes in the valence band would be very high, and this is a energy level which is the Fermi energy level, and it is actually the center of number of charge carriers. What do I mean to say by that is the fact that if we are talking about intrinsic semiconductors, then this energy level will be in just midway, because above and below this energy level, the number of charge carriers, maybe it is electron and maybe it is hole, are equal, which means that if in intrinsic semiconductors we are drawing the Fermi level, then it would be drawn just in the midway, because in intrinsic semiconductors, the number of free electrons in the conduction band and number of holes in the valence band are equal. But in extrinsic semiconductors, like in p type of semiconductors, we can say that this energy level will be very, very nearer to the valence band, due to the fact that the number of holes in the valence band is very, very larger than the number of electrons in the conduction band. And you also know that center of mass always is nearer to the heavier masses. So if the number of holes in the valence band is greater than the number of electrons in the conduction band, then we can say that this Fermi energy level will be very nearer to the valence band. Now this energy level is also representing the energy of these acceptor ions. So this is aluminium ion, and this energy level is also representing the energy of these acceptor ions. This energy is equal to the energy of these ions. Now in N type of semiconductors, you can see that silicon is being doped with group 15 elements like phosphorus, and as you know that in phosphorus atom there are 5 electrons in the outermost shell. So 4 electrons forms the covalent bonds with the surrounding silicon, and 1 electron is free to move here and there, and therefore phosphorus donates an electron to the crystal, and this electron is free to move, so it is represented in conduction band, while the holes are represented in valence band. Now as you know that in this crystal the atom is donating 1 electron, therefore we would say that there would be a positive charge on this atom as it has donated the electron, and the electron which is free to move would be represented in conduction band. And as one donor atom is donating 1 electron, so there are many number of free electrons present in the N type of semiconductor, and some few number of holes present in the N type of semiconductors. So we can say that P type of semiconductor has majority charge carriers as holes, and N type of semiconductors has majority charge carriers as electrons. And we can say that P type of semiconductors has minority charge carriers as electrons, and N type of semiconductors has minority charge carriers as holes. So this is the basic of extrinsic semiconductor. And let me also tell you that in extrinsic semiconductors, when we dope the external impurity, then that crystal does not become charged, which means that some students gets confused by this name, that P type of semiconductor means positive type of semiconductor, because it is positively charged semiconductor. This is absolutely incorrect. It is not mentioned anywhere that P type means positive charge, but generally we can refer that P means positive in semiconductor. But in P type of semiconductor or in N type of semiconductor, crystal is neutral only. There is no change in the charge of the neutral crystal after doping, because the atom which we have doped is bringing the equal amount of positive charge as protons which are present in the nucleus of that atom. So there is no additional charge which is seen on the crystal, and doping does not charge the crystal. So even after the doping, the crystal remains neutral. Okay, and it is just for writing the notes that majority charge carriers in P type of semiconductors are holes, and majority charge carriers in N type of semiconductors are electrons. And there are some free electrons also present in P type of semiconductors, and those free electrons behaves as a minority charge carriers in P type of semiconductor. And there are some holes also present in the N type of semiconductor, and those holes are called as minority charge carriers in N type of semiconductors. Now P type of semiconductor is being doped with a trivalent atom which accepts 1 electron from the surrounding silicon or germanium and makes a hole at that position. Therefore they are called as acceptor ions, and the charge represented on those ions is negative. while in n type of semiconductors, pentavalent atom is doped, which means that they donate one electron to the crystal, and therefore a positive charge is represented on those atoms, and those are also called as donor atoms. Now, this is the same point which I have already discussed, that after doping also there is no charge which is seen on the crystal. So crystal remains electrically neutral even after the doping. And this is very important point, that the mobility, as we have already discussed in intrinsic semiconductors, that the mobility of electrons is greater than the mobility of holes, because we know that while we refer the electrons, we are referring to the free electrons, and while we are referring to the holes, we are referring to the motion of bonded electrons. And obviously the motion of free electrons will be more faster than the motion of bonded electrons. So we can say that the mobility of free electrons is greater than the mobility of bonded electrons, and therefore the mobility of free electrons is greater than the mobility of holes. And in p type of semiconductor, the majority charge carriers are hole, and in n type of semiconductors, the majority charge carriers are electrons. So we can say that the conductivity of n type of semiconductor is better than the conductivity of p type of semiconductor, due to the electron which are present in the n type as majority charge carriers. Now, as we will increase the temperature of extrinsic semiconductors, more electron hole pair will be generated by thermal agitation, in which electrons will jump from the conduction band to the valence band, leaving behind a hole. And in this process, if very large number of electron hole pairs are generated, then we can say that after very large thermal agiation, the number of electrons or number of holes are almost equal, not exactly obviously, but are almost equal, and therefore we can say that the extrinsic semiconductor will behave like intrinsic semiconductor. The temperature at which this happens, when the extrinsic starts to behave like intrinsic semiconductor, is called as the critical temperature, and the critical temperature for germanium is 85 degrees Celsius, while the critical temperature for silicon is 200 degrees Celsius. It is obvious that the germanium is having the low critical temperature, due to the fact that you know that germanium has a forbidden energy gap of only 0.7 eV, while the silicon has a forbidden energy gap of 1.1 eV. So it is more difficult in silicon for electrons to jump from valence band to conduction band, and hence a large amount of temperature is required for that in silicon. Now, if we talk about the p type of semiconductor, so if we write down the value of current in p type, so we know that in p type semiconductor, the number of holes are majority charge carriers, and it is obviously, this is concentration of holes, which means the number of holes per unit volume. So it is very greater than the number of electrons, because electrons are minority charge carriers in p type, and it is almost equal to the acceptor ion concentration, which means that we can say that the number of acceptor ions per unit volume is almost equal to the number of holes per unit volume in p type of semiconductor, and therefore the current flowing in p type of semiconductor will be mainly due to the holes. So we can say that it would be NH, which is the number of holes per unit volume, EAVH, where VH is the drift velocity of holes. While in n type of semiconductors, we can say that number of free electrons are very greater than number of holes, because electrons are majority charge carriers, and the number of free electrons per unit volume is almost equal to the number of donor atoms per unit volume. And in this we can say that I current will be mainly due to the flow of free electrons. So I will be NE into EAVE, where V is the drift velocity of free electrons. So this was the complete analysis of extrinsic semiconductors, and in the next video I will be bringing the most awaited topic, which is diodes. Thank you.